In this video, we're going to look at how to use the individual half reactions of an overall redox reaction to balance that overall redox reaction. So the simplest way to explain how to do this is simply to take the redox reaction and break it into the two separate half reactions, which is relatively easy to do. We can see that OS and OSO4 are the only compounds that contain osmium, and likewise the polyatomic ion iodate and elemental iodine are the only two species that contain iodine, so these make up the unbalanced half reactions. Now, since we're balancing this in acidic solution, we can follow all four of the steps to balance each of these half reactions individually. So let's do each of them at the same time and see if we can save some time. Since both the reactants and the products of the first half reaction contain only one osmium, we're done balancing the major atoms in our first reaction. However, we can see that in our second reaction, elemental iodine has two iodine atoms in it, so we need to balance the iodine in the reactants, but with a coefficient of 2 here. Next, we need to add water to both reactions in order to balance the oxygens. So in our second half reaction, we have a total of 6 oxygens, so we would balance by adding 6 water to the products. And likewise, for our first reaction, there are 4 oxygen atoms in the products, so we can balance this out with 4 water molecules in the reactants. Now, as a consequence of adding water to both sides, hydrogen has become imbalanced. So in our first half reaction, we have a total of 8 hydrogens, so we can add 8H plus to the product side like so. And we have slightly more in the second half reaction. We have 12 hydrogen atoms in the products, meaning that we can add 12 H plus ions to the reactants like so. The final step in both cases is to balance out the charge. So in the first reaction, we see that our reactants have a total charge of 0, meaning that we need to add electrons to the products in order to cancel out the positive charge from the H+. We have 8H+, which means we need to add 8 electrons in order to cancel this charge. Now, it's tempting to add 12 electrons to the reactants in our second half reaction, but that would be a mistake as we need to consider the -2 charge of the 2 iodate polyatomic ions here. So we can see that positive 12 minus 2 is positive 10, meaning that we need to add 10 electrons to the reactant side in order to balance out the charge. At this point, each of our half reactions has been successfully balanced, and if you keep in mind one of the tips that we used when writing complete redox reactions for the purpose of calculating voltage, we saw in that case that we need to cancel out all of the electrons in the reactants and the products. In order to do this, we simply need to find the lowest common multiple that each half reaction can be multiplied by in order to find that common factor to equalize the amount of electrons. And again, we do this simply by counting the number of electrons in each half reaction. So we see that 8 electrons in the first half reaction and 10 electrons in the second half reaction. The lowest common multiple that I can think of is 40. So if we were to take our first half reaction and multiply it by 5, because 8 times 5 is 40, and if we take our second half reaction and multiply everything by 4, 10 times 4 is 40, meaning that we have the same number of electrons in the reactants and the products, which means that they should cancel each other out. Now, the tricky part is making sure that we do this with every other reactant and product in both of our half reactions. So let's go ahead and do that below. So if we write out the reactants for our first reaction, half reaction, multiplied by 5, that means we would have 20 water and 5 osmium. And then if we do the same thing for the second half reaction, we have our 40 electrons. 12 times 4 is 48 H+, and then 2 times 4 is 8 of the iodate polyatomic ion, and that should be all of the reactants from both half reactions. Next, we need to do the same thing for our products, so we would have 5 osmium oxide here, and then 5 times 8 is 40 H+. Let's deal with the canceling after everything is written in. 5 times 8 is 40 electrons, which is exactly what we expected it to be. And then if we add the products for our second reaction in, we would have 4 iodine, and 6 times 4 is 24 water. Now we can simplify this reaction by canceling the compounds that we have in both the reactants and products, starting of course with the electrons because we have exactly the same amount. We can see that the 20 water will be canceled in the reactants, and we will cancel 20 water in the products, meaning that we'll have 4 water left over. And likewise, we would cancel the 40 H+ in the products, and canceling 40 H+ in the reactants, we would have 8 H+ left over. So if we rewrite this in simplified form, we would have 5 osmium, because that doesn't get canceled out, plus 8 H+, plus 8 of the iodate polyatomic ion, which would then go to 5 OSO4 plus 4 diatomic iodine plus 4 water. And you can see, not only do we not have any electrons written in this overall equation, because the number of electrons that are gained by the reduction reaction is equal to the number of electrons lost in the oxidation reaction, so the charge balances itself out here. We can also see that the charge is balanced in the overall equation, because we can see that our products have no charge at all, and the positive 8 from the H+ is canceled by the negative 8 from the iodate, and if you count up the individual atoms, you'll see that our mass is balanced as well. So in summary, when it comes to balancing an overall redox reaction, it's a simple matter of balancing out the oxidation and reduction half reactions individually, finding a common factor by which to, or the lowest common multiple rather, and multiplying by common factors in order to get each electron count to the lowest common multiple, adding everything together and canceling out any species that appear on both sides of the reaction. In the next video, we'll go over an overview of how to do this using basic electrolyte rather than acidic electrolyte.